Hello, everyone, and welcome to today's webinar, Explainable Data Science Workflows. I'm Julia Moeller. I'm joined here by today's Austin Iovito, data scientist at IBM. Before we get started, I wanted to cover a few housekeeping items. So we welcome your questions today. You are in listen-only mode, so if you have any questions, please type them into the GoToWebinar control panel on the side of your screen there, and we'll answer all questions at the end of the webinar. And if you have any technical difficulties, please contact me and I'll try to help you out. My email's there on the screen. And finally, out the recording for today's webinar. So you should receive that within the next couple of days. And at this time, I'd like to turn it over to you, Austin.
Awesome. All right. Thanks everyone for attending. Big shout out to Data Science Salon. Thanks for this opportunity. Really appreciate it. And I hope everyone's happy and healthy right now during these times. So, but yeah, once again, thanks for being here, and we'll kick this off. I guess a little bit of background on me. So I'm a data scientist at IBM, and the motivation for this talk is to serve kind of as a primer of how explainability could impact your current workflow or your future workflows, and kind of free up time that is attributed to downstream tasks and refactoring code. So to motivate that, here's three quotes that are pretty popular. So you've probably heard them before. So there are three kinds of lies. There's lies, damned lies, and statistics, popularized by Mark Twain. No one's really sure who said it. There's the George Box, all models are wrong, some are useful. And then really the focus of this talk is, why did you do that? And really anyone could say that, from your end user to your manager to a fellow data scientist to the C-suite and beyond. So that's really our focus area for today, is how do you codify and relay your findings in an intuitive manner. So why you're here so by the end of this talk, you will understand the motivation and the reasoning behind this graphic and the information it communicates to those stakeholders that we just went over. This specific image is from the LIME algorithm, which is a local interpretable model agnostic explanation, and we'll talk about that more. This is a algorithm that was invented outside of IBM. There is a paper describing it, but it is wrapped in the software that I'll be demonstrating today. So under the umbrella of explainability, there's two terms that are often used interchangeably, and I like to differentiate between them. And those two words are interpret and explain. Although very similar, they are different, and I'll give you a little background on why and how, how we came to that conclusion. So here's the definition of interpretation interpret from Merriam-Webster, and we're really focusing on the first portion of it, to explain or tell the meaning of, present in understandable terms. And we further define interpretability as a static component of the explainability paradigm, meaning if you have some kind of predictive model that outputs some probability, then you would use that output as an interpretation. You would interpret what your model's doing in a static environment, and then you could use that reasoning to go back and fine tune your model, what have you. Explain is to make known. So explainability is dynamic. So you would get that output from your model, interpret it, and then go back and refactor, and dynamically do that until you reach your end goal, or you satisfy your end user. And that is the explainability paradigm. So the idea is, don't just code for the end result, code to make sure that your intuitions are well known and that your team and stakeholders and end users are aware of what is happening. In industry and in a productized environment, this portion can be there's a few portions that are outside of the scope of this talk, but when we talk about IP, GDPR, things of that nature, there's only so much you can relay to certain stakeholders. So that is something that you want to be aware of. So what is the high level from that? So what we want to do is we are going to define explainability as the ability for data scientists' results to be understood and interpreted by their data scientists and stakeholders. The real idea and motivation behind this facet of explainability is the idea of your work should not be happening in isolation. You really want to be wary of, what are you doing? How does it impact, the other moving parts? And are you aware of, the problem you're solving? And does what is the code you're creating solving that problem? So the idea is you want to create, an applicable solution in a timely manner that actually meets the requirements set for you. I'm sure everyone has stories of their own where things may become slippery, or maybe some assumptions are hard to communicate across teams. So that's why we're really focusing on, this at a micro level rather than a macro level, because the idea is this should not redefine or really, have a large change in your workflow. What it should do is it should augment your current workflow and make your job easier. Because what we don't want to do is take a complex topic and, solve it with complex solutions. We'd want this stuff to be as approachable as possible within reason and the scope of what you're doing. And so this graphic, we were talking about our end user. And so what this graphic is trying to describe is our x-axis is, you can think of that as experience. You can think of the z-axis as the need of the user, and then the y-axis is the technical skill. And as you can see, we plotted a few different stakeholders on this. So you have a data science manager, or that could be a business analyst manager, what have you. And the idea is that this is someone who is both technical, experienced, and has high need, i.e. they need as much transparency as they can in your product, so that way when they relate to their stakeholders or upper management, they can adequately do your product justice. On the flip side, we have fellow data scientists. So that may be someone whose technical skill could range from 2 to 5. Their experience is probably less unless they're like senior data scientists, and their need is not necessarily like paramount. I.e. like they may not need your code, or they may not need that product in their hands as quickly as some of the other people. Then on the other side, you have a regulator, someone who may not necessarily be super experienced, but is relatively technical and has high need. And then lastly, you have your end user, someone who may not, understand the technical aspects of what you're doing. They may not understand, they may not have the experience to understand what the use cases are, but they're the person who's going to end up using your product, so their need is high. And the idea is explainability should be approached from a facet in which you are building it out for one of these end users, because obviously no solution is going to satisfy every audience. So what this tries to do is segment the persona of who you're building your product for, and that will help you scope your work using this software. So for the example that we're going to go over, it's the Portuguese banking data set from the UCI database. And the problem associated with this data set is to classify whether or not users opened or did not open a bank term, and then to identify the principal factors to contributing to this classification. An interesting point to make right here is this: you could codify this as explainability, because the idea of this problem is we're going to classify users. What that actually does, though, is that makes the assumption that our predictions are valid, and we are actually, when we classify a user, we are making the action on behalf of the person who will use our product, versus the prediction just relays information where a human could make a decision. So that is something, I'd argue is a facet of explainability, is, defining your problem. At least on my team, we kind of move under the assumption, a well-defined problem will yield a well-defined solution. A poorly defined problem will yield a poorly defined solution. And the idea behind that is, really, kind of treating this like the scientific method. Codifying, relaying your assumptions, making sure that, you're not violating them. And if they do change at any point in time, you capture and relay that to, the people who need to know. So this is the code. This is from Lale, which is an IBM open source toolkit. And what it is it's built on top of sklearn, and it makes use of different cache algorithms. What cache stands for is combined algorithm selection and hyperparameter tuning. So if you've used the sklearn pipeline features, this looks pretty similar. It is basically an extension of sklearn, and then it has a few novel functions. So for instance, we can use the double greater than sign and the vertical bar to denote, a chain. So the first line is basically saying we're going to make a union between a principal component analysis and no operation. We're going to concatenate those two pieces of data, and then we're going to optimize a logistic regression, a nearest neighbors, and a tree to see what yields the best results. And we can visualize this. The second line is where we are configuring on our training set. So you can think of this as this is the fit. So sklearn, the model fit predict paradigm. This is we instantiate our pipeline, which is our model. Then we configure it, which is the fitting. We can choose different scoring metrics. So in this case, we wanted accuracy. If it was regression, we could use like R-squared, things of that nature. And then we're using hyperopt as our optimizer, which is Lale uses hyperopt, SMAC, grid search, CV, things of that nature. I chose to use hyperopt because it was the most robust for this data set. And then our best loss is 93. Our best loss is the negative accuracy. So when we visualize our pipeline, you can see the description I just gave you is relayed through this graphic. And then the interesting part is we can print out the hyperparameters for our optimal pipeline using the function. And we can see our PCA uses the RPAC solver. It does whiten. It's outside the scope of this because I'm just trying to show you guys, simple workflow, but you can manually change each of these models that you insert and your transformations as well. So you can basically change the schema of the PCA. So you could set a maximal amount of components, a minimum amount of components. You can do the same thing with the nearest neighbors and the trees. You can fine tune their hyperparameters before you feed them in. This is just showing you, a purely automated workflow. And the idea of this is not to necessarily do this and send it into production, but it helps you prototype in a more cogent manner. And the other thing is that this is portable and it is stable. So when I pre-print out my hyperparameters, you can just store that in a JSON, send that, push it to Git or what have you, whatever you may use. And another data scientist could pull that out and run your algorithm on another machine. And that is a strength of this, in that it's stable across, different operating systems, things of that nature. And then we can see the accuracy of this pipeline is around 69%. State of the art for this data set, I'm pretty sure 76%. So, with, 5 lines of code, we were able to get within, 10% of the state of the art accuracy, which is not necessarily impressive, but it does show, we could just run this a few times, see which algorithm works best, and then, build out a class that uses manual hyperparameters for our deployment. And so this is the image of the prediction probabilities. So the way we obtain this is on the next slide, but basically what this is telling you is based off of the data set we fed in, what features indicate, a classification of 0, which is not opening a term, or 1. So this is for a specific observation, and basically what it is saying is, I guess it's good to tell you, since this is a binary classification problem, just based off of the rules of probability, the log probability of class 1 is going to be the inverse of the log probability of class 0. And so what that really means is you can see for a classification of value 1, duration with a score of less or equal to 100 contributes approximately 5% to the classification, versus if we're going to classify this as, they did not open their term, or, 0, duration, if duration has a negative 0.05 contribution, if it is greater or equal to 100. So yeah, so that's just, a quick way of making sure that the math checks out. And what produced this score, what produced this table, you can find this in the GitHubs I sent you that are at the end of the class, but there's a lot of resources on the GitHub as well as the masterclass that I've been alluding to that will show you how to build this out and deploy it. It was just for the scope of this talk and the length, I decided not to show it. And then these are two metrics from AIX 360, which is the open source software for explainability from IBM. And there's two metrics. There's two papers that relay, the mathematics and assumptions behind each of these models. But what's happening here is we're trying to see if our model, if our explanations model is faithful. What that means is when we use Lime, it is taking a local interpretation. And what that actually means is it takes our data set and perturbs it slightly and sees how that modifies the predictions in from the model. And we backwards propagate that. It's a linear model, and we're able to see is Lime computing what our original model is. So if we go back a slide, when we use Lime to see how the explainable pipe works, faithfulness tells you if our optimal algorithm is a tree, when we obtain our explanations, which is this graphic, faithfulness relays if Lime and the decision tree are computing the same computations. And in this case, with faithfulness at a very small negative number, almost zero, it tells you that we are not computing the same algorithm. And this is an important point because there's a lot of literature, especially out of Duke University. One author, her name is Cynthia Rudin. She and her colleagues have basically made quite a few papers and put into the explainability, the sphere of explainability that maybe algorithms like Lime are not the best way to approach explainability. Perhaps we should use directly interpretable models such as a decision tree, a logistic regression, nearest neighbors, things of that nature, because those are things that we can visually inspect. Think of a decision tree, you can see the splits and things of that nature. Even a logistic regression is, relatively explainable because you can, get your coefficients, things of that nature, versus, using a convolutional neural network and then trying to create local interpretations of that in order to, relay why an image may be classified as a cat versus a dog. But moving on, the second metric is monotonicity. And monotonicity is the idea if you have multiple features, each feature is additive to accuracy. So that means like if you have feature 1, 2, and 3, if feature 1 contributes 15% accuracy, and feature 2 contributes 7% accuracy, and feature 3 contributes 5% accuracy, that is monotonically increasing. So therefore it is satisfied. And what this indicates is, the strength of your data set, for lack of a better analogy, is are the features you're including and feeding into your model actually increasing your ability for your model to discriminate between classes or not? And so the idea in this workflow is, these are all static interpretations. Like we run our pipeline, we interpret our accuracy, and we get our outputs, we interpret, it's not faithful, but it is monotonic. So now what we would do to, try and make this explainable is iterate over it again. You can think of this as like an iterative or recursive workflow where we're monotonic, that's good. We're not really that faithful. So perhaps we could, optimize our model, or we could change our hyperparameters, and maybe we could trade off some accuracy to make a more explainable model, or it could be less explainable and more accurate. That idea has not been like mathematically proven. No one can truly say like you're giving up accuracy at cost of explainability or vice versa, just because the nature of the problem is very important, and also the threshold for explainability. So using the previous example, a convolutional neural network that discriminates between cats and dogs, I would argue it does not have as high of a explainability threshold as perhaps, a loan application algorithm would, or you know, recidivism rates in jails. That's quite a popular algorithm that people have written quite about, is the Compass algorithm used in Florida, because it was ultimately biased and unfair, and people couldn't really explain why. And that motivates explainability, because not only will it protect your user by allowing them to, you know, understand what's going on, it'll help protect the business from, you know, putting out software that may or may not be acting in the way the behavior of the algorithm that you deploy may not reflect what happened in development. And that's what explainability is trying to address, is how can we be as aware as possible of issues before they arise, or when they do arise, we have created steps to, you know, alleviate them. And this is all captured in further detail on the masterclass. And then there's a GitHub with this code as well that will be sent out afterwards from Data Science Salon. So a research overview of kind of, you know, some big players in the game. So Stop Explaining Black Box Models, Machine Learning Models for High-Stakes Decisions. That's Cynthia Rudin's paper. It's very good. I would think of it almost as like a critique of, you know, the current trend of using state-of-the-art algorithms wherever applicable, versus, you know, really leveraging your skills and intuition as a data scientist to create the simplest, most performant solution to your problem. You know, there's explainable artificial intelligence, which kind of set the frame for this movement that happened in 2017. That came out of DARPA, which is a government entity. So there's DARPA and IARPA, and they're both heavily funding. I think at least in time of 2017, I think it was like a $3 billion investment to, you know, schools like Stanford, CMU, and a few others. And these groups are basically trying to build out, you know, scalable, explainable interfaces for, you know, both, you know, personal and private use. That's an interesting one to look into. There's a lot of information on it. So I recommend starting there. That will kind of point you to a lot of different areas. Then there's Why Should I Trust You? That is the paper of Lime. It motivates why Lime was created, the mathematics behind it, and its use cases. It's important to note that Lime does work with tabular, image, and text data. So there's examples of, you know, like the 20 news group data set, you know, if something's classified as, you know, if a document's classified under the atheism tag from that data set, it will, you know, provide you the text that indicates that classification, or, you know, if it's hockey, what have you. There's type-driven automated learning with LaLe. That's from Martin Herzl and his team at Yorktown. We have Towards Robust Interpretability with Self-Explained Neural Networks. That's an MIT paper. It doesn't say it by name, but if you are interested in neural networks and things of that nature, and you want to, you know, try and explain them through, you know, isolating, you know, gradient values, things of that nature, that's a more complex and mathematically intensive process, but there are open source softwares to do things like that. Specifically, Facebook's Captum, and Uber has one as well, but the name escapes me right now. And then there's Google Vizier. So explainability, there's a few ones. There's explainability under the guise of you know, just logging and evaluating hyperparameters in real time, and, you know, attributing that to model behavior. And then there's also the explainability of, you know, before you even deploy your model, and, you know, watch for things like data drift and things of that nature, you know, really making sure that your model is going through with computations that achieve the goal you want. Because, you know, this is anecdotal, but from my limited experience that I've seen is, you know, proxy problems can only take you so far if your solution doesn't have data that, you know, is directly attributable to it. So that's one scope of it. And I'm hoping, as you guys see, this is a nascent field that is not necessarily well defined yet. So there's definitely room to, you know, have your say in it. But secondly, it is a high yield area, meaning, you know, the impact of actually implementing these things hasn't necessarily been seen yet. But the idea is, it'll mitigate downstream costs associated with things like refactoring, perhaps something like a lawsuit coming because your model made an inaccurate, prediction because it wasn't doing what you thought it was doing, things of that nature. It's not a panacea. It's not going to fix everything. There are still, issues that you can attribute to just, just smaller scale things, larger scale things. So it is really important that you guys understand this isn't a gotcha for every problem you're going to encounter, but the hopes is if you implement it into your workflow, you will you'll remove some of the redundancy from, the prototyping development stage and pushing into production. Yeah, so this is where the demos live. So there's the AIX 360 Blue Mix that goes through, like, you basically pick your persona. Like, are you a loan? Are you someone who provides loans? Are you like a medical doctor? Things of that nature. And it kind of talks about how AIX is built out to address each different persona. It includes 10 different algorithms. 8 of them came from IBM. 2 of them are just wrapped. Specifically Shapley values, which is based on game theory, and then Lime. But the rest of them were created by IBM. So you have things like contrastive explainers. You have things like rule-based explainers, where basically you can feed your data set in and it'll try and build, a logic-based handle it. There's also, it's called Proto-Dash. What Proto-Dash does is basically it gives you a prototypical example of your data set and the classification it would receive. What that does is it helps you frame how your model is actually ingesting the data. And then, moving forward, there's the GitHub as well that has, demos, talks, things of that nature. The masterclass also has there's a webinar from the principal researcher Dennis Way from Yorktown. That's on the masterclass link, which is the last link. There's the Lale GitHub, which is, github.com, IBM Lale. That's another bunch of examples. I really like their examples. I've worked with Martin closely. One I would point people to directly is the Lale for sklearn users, because most people are familiar with sklearn, and it has a pretty acceptable learning curve if you haven't used it before, and understanding of the sklearn environment will translate almost directly to Lale. There's just a few sugary syntax tricks that you'll have to learn, but it's a pretty easy transition. And then lastly, there's the IBM Masterclass. That's something myself and my team put together. What that is it's an hour and 10-minute class. It's 11 sections. It runs you through, data ingestion, feature engineering, creating a Lale model, explaining the model, and then how to write a report and visually inspect it. And there's also a hackathon attributed with that as well, with an $8,000 prize pool for the top 3 winners. And then the last part of that is there's a IBM Skills badge, which you can earn by completing the masterclass, taking the quiz at the end, and then participating in the hackathon. You don't have to win the hackathon to get the skills badge. It's an intermediate level skills badge. So in order to validate a user earning that, we had to make the preconditions more than just taking the class. So that's why the hackathon is tied to that. Yeah, so this is the IBM Masterclass on explainability to that link. And then this is the bibliography of the papers I included and where this information came from. And I'll let Julia take it now.
Cool, thank you, Austin. So we did have a couple of questions come in that I want to address before we let everyone go. So one of the questions was, are there specific explainability libraries for neural nets?
Yes, so Facebook Captum is a good one. Then Uber, there's a specific one from Uber, but there's also Uber Pyros, which is a probabilistic language. People have argued that is explainable because it's derived from Bayesian mathematics. I don't really have a lot of use case with it. I have used Captum, and we're actually building out a demo with Captum that will be published probably by the end of this week. So that'll be on the GitHub. That's linked in the follow-up email, so you can look for that.
Awesome. And then one other one, should I use interpretable models directly or explain uninterpretable models?
It ultimately depends on the use case. So, I mean, the advice I've gotten from like my mentors and things of that nature is, you always want to be skeptical. Like, as a data scientist, you want to be the first person to say like my model's wrong or things of that nature. So the idea is like if you implement your model the first time and get 90% accuracy, you should immediately think, at least I do, what went wrong? Or is this demonstrating the behavior I expected? Things of that nature. And what that'll lend itself to is, once you kind of build up this catalog of knowledges, there are circumstances where, CART, an algorithm from the 80s is more than acceptable. And it's going to give you, pretty robust results. That being said, there are things, like autonomous vehicles where building a rule-based system for that isn't really feasible. So you have to use a neural net. And so I think there's caveats associated with each. It's just being aware of those caveats and the assumptions you're making and, being able to explain it to your stakeholder.
Awesome. And then we also did get an inquiry if we're going to be sending out the slide deck. And yes, we can definitely include that in the follow-up email. And then before we let everyone go, I did also want to reiterate that the masterclass is going to be available until May 1st. And I can actually send that link directly to you guys here in the chat. But it'll also be included in the follow-up email. So be sure and go ahead and attend that. You're going to have a chance to compete in the hackathon and earn your IBM Skills badge. And there's also an $8,000 prize pool for the top 3 winners. So we'll send that along with the webinar recording and the slides as requested. And of course, if you guys have any other questions, feel free to follow up with us after the webinar and we'll get back to you. And with that, thank you everyone for your time. Thank you, Austin. And we'll see you on the next one.
Thanks, everyone.